Okay, so my name is Chris Baker, as Jacob said. I do have a background in both architecture and engineering, which essentially means I can be contrarian talking to either profession. So I'm going to be talking about energy design assistance throughout the design process and intervening earlier in the process to get more energy savings. Margaret Mead, American anthropologist, said, "I was brought up to believe the only thing worth doing was to add to the sum of accurate information." There's a lot of opinions about energy consumption in buildings and how to reduce that energy consumption. We at the Weidt Group feel that energy modeling is one of the most powerful tools we have at our disposal to replace those opinions with facts and numbers, that we can, instead of just arguing principles and what rule of thumb works, we can actually look for this individual building, what is the best option. So today I'm going to be talking about who the Weidt Group is and what we do, and then energy design assistance as a process, how we use energy modeling throughout that design process, and then lastly talking about the accuracy of energy modeling, which I know is a kind of a topic of hot discussion in our industry. I'm having trouble. I don't hear anything on the other side now. Can you guys all still hear me?
Chris, yep. The sound's coming through pretty clear, and we're just muting ourselves so you don't get any background noise. And you got about...
I want to make sure I wasn't talking to myself for an hour.
No problem. And you got about 27 people in the room, a mix of architects and engineers.
Great. Thank you. So the Weidt Group creates tools, and we provide consulting for energy decision makers. Our main line of business is what we call energy design assistance. It's modeling-based design assistance. So we're using energy modeling to explore different options. We work on about 350 commercial buildings per year. Most of those are 25,000 square feet or larger, though we do also go down as small as 5,000 square feet. We do this for 6 utility demand-side management programs and 1 statewide program. We also do it directly hired by architects and engineers, either when they're pursuing LEED or a net zero building or just want to have a high-performance building. We will provide a similar program that we do with the utilities that we work for, just without a utility incentive. The other area we work in is what we call ongoing energy performance. And this is coming back after the building is built, a couple of years after it's been up and running, and trying to find additional energy savings, either because the building is being used differently than they anticipated, or there are newer technologies we can evaluate. Thirdly, we do benchmarking. We have a system called B3 benchmarking, which is being used by Minnesota and Iowa to benchmark 7,600 public buildings. In those public buildings, the reason we're using B3 benchmarking rather than, say, Energy Star is almost 3/4 of the public buildings in those 2 states weren't Energy Star applicable because of the building type. And so they didn't have the capability to enter it into Portfolio Manager and compare it to peer buildings. So B3 benchmarking was created so that these buildings could all be benchmarked to an appropriate baseline for that building type, even if it fell outside of the CBEC survey. And then finally, we have software tools. About 1/4 of our staff, maybe 1/3 of our staff, are software professionals, and we create custom energy modeling tools. We've done things such as EcoNermin, which was for the Bureau of Energy Efficiency in India. It's a code compliance tool that uses web-based energy modeling to show how well an office building is doing, an office building design is doing compared to the code base. We've also done work for McQuay and envelope manufacturer, a building envelope manufacturer that I'm not yet at liberty to say who it is. On average, on the projects we work on, the commercial buildings we work on, we're saving 30 and 46%. The 30% is if we get involved during design development. The 46% is if we get involved in pre-design. The 30% we've actually held fairly steady over 2 large code cycles. In the Midwest, where we have the most work, we had the 1989 code until just about 10 years ago. And then, so we've had 30% better than code when we had the 89 code back in the early 2000s. For the first couple of months or year, when the new code, the 2004 code, was implemented, savings went down a little bit, but now it's kind of leveled back off at 30%, and it's done the same as we come through the 2007 code. It fluctuates year to year. Sometimes it's 28, sometimes it's 32. But by and large, we're getting about 30% energy savings, even as new codes come into effect. We're just now having the 2010 code being adopted in Iowa and Illinois, and so we're going to be watching to see if we can maintain that average savings. In the utility territories we serve, we work on about 70% of the buildings in the applicable size range. So last time we analyzed how we were doing, it was in Minnesota, and we worked for Xcel Energy in Minnesota. Of the buildings over 50,000 square feet, which is what their program cutoff is, we've worked on 71% of the new buildings since we started working. So a fairly broad range of the market. One of the things I think is interesting about having 71% of the market for new buildings, we're working on everything from the, we worked on the Twin Stadium when the new Twin Stadium was built, and they had a very high goal for energy and for LEED in a kind of challenging situation. But we're also working on the new gas stations that are built in town and the kind of smaller run-of-the-mill crank-out projects. So we get a pretty broad perspective on the new construction industry. Next, I'm going to talk about energy design assistance. So this is how we intervene with the design throughout the process to try to move more energy savings into design. Most energy modeling today happens for either LEED points or code compliance. It happens for those two things at the end of construction documents. But modeling for comparative analysis is much more valuable. If we can start that modeling earlier, we can use it for decision making. Now, both ASHRAE, who write the major model code in the nation, 90.1, and USGBC, who govern LEED, are both pushing to have energy modeling done earlier in the process, not just after the construction documents are complete. ASHRAE is working on a new standard called Standard 209. Right now, it is not yet even in draft form. We're working on the outline of it. Standard 209 will be, I always get this title just slightly wrong. It's energy simulation aided design for new construction. So it's going to basically be a companion to 90.1, but rather than you have to do this in your building, it's going to be requirements of, if you want to be 209 compliant, you have to analyze these many options at this point in the design phase. And it's going to have requirements from pre-design, schematic, design development, contract documents, into construction administration. Similarly, USGBC is pushing to have energy modeling done earlier. And the newer version of LEED version 4, which hasn't been published yet, is going to require modeling sometime earlier in the process. I haven't seen the exact requirements. I'm not sure exactly where they've landed on it, but they're moving to have modeling done earlier. As I mentioned earlier, we've been able to see about 30% energy savings on average if we can start in design development. If we start earlier than that, what we call early EDA and pre-design, we've seen it as high as 46. Similarly, if we use modeling after the building is built to help improve the operation of the building, we've seen 10 to 20% energy savings. The range on the ongoing performance is a little higher right now because it's a newer program for us. We've been piloting for the past year and a half or so, and we've done about 6 buildings so far, as opposed to the EDA where we've done over 1,200 in the early EDA where we've done a couple hundred. The way code is written, you start with design, and from that you derive the code base. Well, this means you don't actually know everything about your code base until the design is basically complete. It makes it very hard to use code to help you make energy efficiency decisions if you just strictly model per Appendix G. On the other hand, if you want to use design assistance, if you want to help a design team make better energy decisions, you want to start with a code earlier in the design, even though you're going to have to make some assumptions of what that code is, and test different things out and see what different design alternatives would mean. Put this another way, as a design team, you might be considering 3 different options. And what you want to do is look at A compared to B compared to C. The way code is written right now, the way 90.1 and Appendix G is written, you need to compare each of those options to their own baselines. So this is one of the reasons code-compliant modeling is a little bit different than design assistance modeling. You can't compare to each other's baselines. You can't compare directly to each other. You compare each one to their own baseline. The reason this matters is as you're trying to decide between 3 different options, each of those 3 different options have their own energy consumption, and each of their code baselines have their own energy consumption. And what can happen is option C in this example uses the least amount of energy, but the code of option C also uses less energy. So even though this design option uses the least amount of energy, that bar is smaller than for option B. You get less credit. One area where this becomes a factor is, for instance, how much window-to-wall area you have. You get to take credit for additional daylighting, but as long as you're below 40% window-to-wall area, you're not penalized for the additional load. So even though a 20% window-to-wall area may be the best performing energy-wise, you could get additional savings by bumping that up to 40%. On the other hand, if we compare all of those to a common baseline, or we compare them to each other, the fact that the C design option, the third design option, uses the least amount of energy means it saves the most. When we're talking about the building energy consumption, there's a whole lot of things that affect how much energy a building uses. Everything from weather, schedule, programmatic efficiency, whether there's 5,000 square foot of lobby or 10,000 square foot of lobby, all the way up to lighting power density. Energy Star, for benchmarking the energy performance of existing buildings, takes into account a subset of those items. It doesn't take into account the building schedule or the weather, and that makes sense. We don't control the weather. We shouldn't be able to claim additional energy savings because a particular year happened to be more mild. I'm not sure how your winter has been in Idaho, but our April here in Minnesota has been about 40 degrees colder than it was last April. There was a day last week where last year we had 90 degrees, and this year we had 30. That isn't, the buildings are using more energy, but it's not because they're performing worse, it's because they're being used more because of the weather. Appendix G has a smaller subset than Energy Star that it accounts for. And strictly speaking, code compliance, which is done with the energy cost budget method for the current version of 90.1, has an even smaller portion, which means things like building orientation, HVAC systems, glazing area, building shape, programmatic efficiency. All of these things are decisions that are made very early in the process, have a very long-term effect on the building energy consumption, and aren't really fully accounted for if we're just doing code compliance modeling. So what's the solution? What do we do instead of just code compliance modeling after construction administration? Well, we at the Weidt Group think that energy modeling should be done early and often. And yes, early on, you're starting mostly with assumptions. We like to start modeling as early as well, before the drawings even start, pre-design. We can run a model and have a pretty good idea of how much a building will use energy-wise just by knowing the building size, the building type, and how they're going to use the building. So even without knowing how they're going to, what the floor plan is going to be, if it's a school, you can probably calculate within 20% what the energy consumption will be per square foot. As we know more about the building, we refine those models and we get more and more accurate predictions until finally the building is operating and we can model based on how they're actually using the building and what the actual weather is and see, is the building performing as well as it should? And we can use that as diagnostics. We can use that to find out if the HVAC system, if something's going awry in the HVAC system, or identify additional opportunities for savings of. We had a project recently where it was a speculative office building, and when the tenant leased it and moved in, they put in data closets on each floor that weren't anticipated originally. They took what were storage rooms and put in data rooms. That caused a major difference in the energy consumption of the building and creates the opportunity of putting in data center cooling rather than using the overall VAV system, which would save $50,000 or $100,000 per year. So when we do this iterative energy modeling, we need to have the design team and the owner involved. The design team, we need to have the architect, mechanical engineer, an electrical engineer, and a cost estimator. What we have found is we don't have all of those people at the table when we have the discussion of what makes sense for the building. Any one of them can torpedo what might make a lot of sense for the building with a shrug or by just saying, well, I don't know about that. But if they're all at the same table, and instead of just saying, well, that would save energy, that item will save $12,000 a year or $50,000 a year. We can have a very productive conversation about what their concerns are, whether those concerns make sense for this application. For instance, several years ago, we were having conversations with people who didn't want to put occupancy sensors into buildings because the very first generation of occupancy sensors didn't work very well. 3-4 years ago, we were having a similar conversation with daylighting sensors. As those technologies have matured, though, they're becoming more robust and they're working more effectively. We also need the owner at the table for these conversations because ultimately it's their money that we're spending. We are all familiar with the Architecture 2030 challenge. One of the things I've always thought was interesting about that is the architects are signing up for it and the engineers are signing up for it, but it's not their resources they're committing to it. You can pledge to have a building that's 50 or 60% better than a typical existing, but if the owner doesn't see that that's financially worthwhile for them to invest in, you're not going to have a building budget that will support that. When we do consulting on commercial new construction, we have what we call 3 different tracks. We have Net Energy Optimizer, which is for smaller buildings, more typical buildings, and with a preset list of strategies. We have Energy Design Assistance, which is when we get involved during design development, and it's the 3-meeting process. And then we have Early Energy Design Assistance. So I'm going to walk you through what those 3 different tracks look like and talk about what type of buildings we enroll in the different tracks. And as I mentioned, most of the time we're doing this as part of utility demand-side management programs, but we also do it directly hired by architects and engineers. Schedule-wise, to do the whole process, the early energy design assistance through energy design assistance takes a couple of months, 2-3 months. The pre-design meeting, it takes about a week to get ready for, to do the first round of modeling. We can do massing analysis in 2 weeks. Daylighting and HVAC can be done at the same time in 3 weeks. And then the building system optimization is 4 to 6 weeks. Buildings that are on a shorter schedule or are a more typical building type, if it's a kind of a normal office building or a normal school, we can do with that tool I mentioned, NEO, that I'll be talking about later. And that whole process takes a week to 2 weeks. So our first intervention is what we call pre-design analysis. This is ideally before they've started drawing, and we like to be involved in one of the early charrettes as they're talking about the building. And what we do is we take a typical version of whatever building they have. So if they're doing a school or an office, well, we've done a couple hundred of both of those building types before, so we know what most schools look like from a thermodynamic standpoint. We create a model based on the building size, the location, and the building type, and we run about 50 to 70 strategies on that. And those strategies are everything from building aspect ratio, so how skinny versus how squat the building is, to we have 6 different mechanical systems: ground source heat pump, water-cooled chillers, DX system, air-cooled chillers, chilled beams. And we see on a typical version of your type of building in this climate how well two different types of technologies perform. It's a gross estimate at this point. If you notice, we have on the total KBQ savings, we have a range for each of those strategies because we don't know exactly where it will fall, but most buildings will fall within that range. And we let the design team basically create with us these different bundles, and by pressing these green buttons, we can move and change the different strategies that are in the design options, the bundles, and see what their impact on the energy consumption would be just live in that meeting, and create different combinations and see what type of effort it would take to get to different levels of savings. The next step then is to do massing analysis. We ask the architect to provide us 3 or 4 different building shapes, building massings that they're exploring for the project. And we will model those with 2 different mechanical systems with and without daylight. The reason we do them with both 2 different mechanical systems and with and without daylighting is we have found different building shapes are preferred by central mechanical systems versus distributed. So the exact type of mechanical system isn't as important as if it's a central VAV system versus a unitary system, whether that be water source heat pump, ground source heat pump, or just individual units. The other thing is daylighting. A building, if you include daylighting in this analysis, you're going to end up with narrower floor plates because the daylighting is, reducing the electric lighting load with daylighting provides additional savings. The daylighting opportunity, unlike most strategies, varies significantly based on the building shape. Other types of strategies tend to hold fairly constant. We look at massing with KBTU per square foot, energy cost, and then carbon emissions, depending on which one is the major driver of the decisions for the owner. Will change which way it goes. What we found is most of the time the carbon emissions and the energy cost are fairly correlative. The KBTU per square foot a little less so because the heating, particularly if you're using natural gas heating, is relatively cheap and has very low carbon emissions, but from a KBTU standpoint is actually a little higher than electricity. The next step then is we have the design team select one of those options and we start daylighting and HVAC analysis. With daylighting analysis, we're looking at it in 3 different ways. We have a daylight factor analysis, a sun control analysis, and then for buildings that need more in-depth daylighting analysis, we're going to full radiance. For most buildings, the daylight factor works very well, and we can do a daylight factor analysis in real time during a meeting, or we can go and prepare a presentation and show different design options and what the daylight penetration and the amount of daylight would be available under different sky conditions. For the sun penetration, what we're trying to look at is we're using graphs where the time of day is on the horizontal axis and the month, and then we're looking at either the 15th or the 21st of each month, whether or not you would have sun penetration hitting the work surface. And we can test different shades, fixed shades, movable shades, and see what would you need to do to shade spaces facing south, east, west, and then north obviously is not a sun penetration problem. And then if there's a more complex shape, if you're trying to get light in from multiple directions, we will go to a radiance analysis. The radiance analysis can take as few as 15 minutes to run, but a more complex geometry with a higher quality rendering can take several hours or overnight to run. So the daylight factor analysis is much quicker. You can get a quicker turnaround, but the radiance analysis works well if you need that type of really detailed, high-fidelity calculation. As we're doing the daylighting analysis, we mark up the floor plans with where the potential daylighting is in the current design, and then where we could add additional daylighting, either by adding clear stories or skylights. And then we look at how many square feet that would represent and what percent of the total floor area and the total occupied floor area. And again, the whole process is about nudging the design team gently to greater energy efficiency. Simultaneous to that, we do HVAC analysis. We look at three to four different HVAC systems. We're doing this during schematic design, and what we're trying to do is look at, is a central water-cooled chiller and boiler versus a ground source heat pump or a split system DX? Which of those system types make the most sense? We're not necessarily trying to decide all of the bells and whistles that will go on that system. You might not be deciding whether or not heat recovery makes sense or a VFD on a certain piece of equipment makes sense at this point. But more understanding the overall, whether it should be a distributed system, whether there should be a well field, the big picture decisions that the design team needs to know to continue on their design. If they're going to have distributed heat pumps, it's a very different architecture. You need closets for those, or you need to figure out if you're going to put them in the plenum. As opposed to if you're going to have chillers and boilers, you need a large mechanical room to put those in, and then the VAV boxes will probably just be in the ceiling. We look at this with energy cost, kBTU per square foot by end use, emissions, and finally life cycle cost. Most owners are deciding it based on life cycle cost. That takes into account the expected rate of escalation for fuel, whether or not, what the incentive from the utility will be, the difference in operations and maintenance. What we have found is most buildings, the operations and maintenance, which is the most difficult item to estimate, even if we multiply that by a factor of 10 from what we think it will be, it doesn't have that large of an impact compared to the first cost and utility cost. Those are the two items that have the overwhelming impact when you extend it out 25 or 50 years. So that's what we call early energy design assistance. Projects that participate in early energy design assistance, we then feed into energy design assistance. Energy design assistance, we start in either late schematic design or early design development. Projects that don't participate in early energy design assistance start at the energy design analysis. For this, we have a 3-meeting process. First, we agree on what we're going to consider strategy-wise. We set a schedule. The second meeting, we review the individual results, and we create bundles of strategies where we combine them and watch what they will do as they interact and what the cumulative savings of, say, 12 strategies would be compared to 17 strategies. And then we have a final meeting where we ask the owner to select one of those to implement. So in that first meeting, we typically are looking at 50 to 70 strategies in about 10 to 12 major categories. We try to always look at more strategies rather than fewer. So we don't want to not look at something just because the design team is a little hesitant. We want to see what the energy savings will be. We think that helps. Well, we've seen that helps them consider the item in this project as well as starting to become familiar with it so that in future projects it's more likely to be included. The other aspect there is when you can put a fairly confident savings number to an item, something that didn't sound all that attractive in this first meeting, if you can come back and say, well, that item we were talking about would save $72,000 a year, that starts to be something worth considering quite often. We also try to bracket energy savings. So instead of just looking at the expected wall insulation level, we want to look at insulation levels beyond that and below that to see what is the sweet spot, what's the appropriate, the most economic combination of strategies and the most economic amount of insulation, because it might be more than we thought or it might be a little less depending on what that response curve is. At that second meeting, we have an exercise very similar to what we do in the pre-design, where we are actually moving these buttons around and creating bundles of strategies. So saying, okay, if we do this combination of things, we'll save 28%. If we do this next combination of things, we'll save 33%. We're doing this live in the meeting so the architects and engineers and owners can see what happens with different combinations. We think that's important to get their buy-in from the process. If we just told them, what we have found is if we just came in and said, you should do this combination of things and it will save 33%. If you do this other combination, it will save 28%. They're less likely to either accept that option or to fully implement it than if we let them participate in the process. And as I mentioned earlier, we're getting on average 33% or 30% savings on the projects that do just this part, and 46% on the projects that participate in the early. And then lastly, we come back at a final meeting and present a report with all of those the 3 or 4 options and ask the owner to select one of them to implement. An alternative process to early energy design analysis or energy design analysis is Net Energy Optimizer. We developed Net Energy Optimizer to serve smaller buildings and quicker schedules. So we're using a web-based energy modeling tool to look at what the integrated energy savings are for a abbreviated list of building types. So we selected the building types we do the most often, and we're continuing to expand this list. We'll be adding 3 more building types in the next 2 weeks. We don't always move that quickly, but in the next 2 weeks we'll be rolling out 2 or 3 more. With Net Energy Optimizer, very similar to the energy design assistance process that I talked about. The difference is it's a preset list of building types and a preset list of strategies. So this allows us to run all of those models in a week rather than hand creating the models and taking 4 to 6 weeks to do all the modeling. We've been using this in 2 of our utility service territories and have the response has been great. The design teams like the speed of it. We are getting a list of additional strategies that we're going to be adding to this and additional building types to try to make this closer to the functionality that we have with the energy design analysis. For all of the projects that we work on through utility programs, and the majority of projects that we work on when we're hired directly by the architect and engineer, we also do a construction document review where we check how much of the savings they said they were going to implement are actually implemented. And then a verification of that, where we walk into the building and we check, are the things they said they were going to do there and functioning? What we have found is some buildings there's additional, some buildings there's a little less. On average, it's 10% less savings than they anticipated. So 90% of the total savings they anticipated are actually installed in the building on average. So looking at that as a whole process, what we have found, design teams always tell us they intend to design a building better than code. How much better than code? It's fair to say that there's not a real good way to put a number to that before we actually start influencing the design. say it's 5% better than code. We then work with them to find what the most cost-effective way to go further is, and we're getting them up to about 33% on average. We then check on that and see how well it was actually installed, how well it was actually put into the construction documents. And we check both at the construction documents and at verification. At both moments in time, what we have found is just by tapping them on the shoulder and saying, this is what you told us you were planning on doing, you've achieved 80% of that, or you've achieved 70% of that. The design team and the owner then go back, either put out change orders or get a few additional things functioning, and it comes back up to about 90% of the savings that they originally anticipated. In theory, then, that amount of performance continues on indefinitely in the building. The real world, a little messier, though. For one thing, we know that every couple of years, code becomes more stringent. And it's not even as gentle or as standard of a stair step as this. It fluctuates. Each code has a different amount of savings than the previous code. So when you have a design, it's operated, it meets the code when it's built, and if it's 30% better than code, it might continue to meet the code over the next couple of years. But in actuality, a lot of times the building may not quite perform as well as we had hoped. The models are based on the building functioning, and that the equipment is well maintained, and that people are using the building as they said they would. If they don't maintain that equipment, or if they change the set points to something less ideal, that energy performance is going to slip a little bit. At times, people will bring it back up, and then at some point there might be a renovation which brings it up to the new code, and then it might slip again. What we're trying to move towards is using energy modeling to have continuous improvement in the energy consumption of the building. So by monitoring how the building's performing compared to how we thought it was going to perform, we don't have that slide back, that we can continue to look at that and continue to improve the performance over time. And so we're working on processes and tools to help design teams throughout that process, through the benchmarking tool that I've talked about, through the ongoing performance track, trying to get additional energy savings. So all of this is kind of predicated on the idea that the energy modeling is accurate, which depends on which audience I'm talking to, whether or not that's something is an assumption that they agree with. There have been a couple of studies with looking at lead energy modeling and comparing it to the actual metered energy consumption of buildings to see how well are lead buildings predicting the energy consumption. I'm going to talk a little bit about why I think those studies are flawed, and talk about a couple of studies that we've done at the Weidt Group to see, at least for our own building that we're working on, how well they compare to predicting. So I'm going to talk about two different populations of buildings in this part of the presentation. For one of our utility clients, Alliant Energy in Iowa, they asked us to look at the 14 first buildings we did with them, which was the first year's worth of buildings. A couple of years later, 3 years after we started working with them, what we found is that if we just updated in the model the weather, we were within 3% of the predicted site use over those 14 buildings. If we updated the hours of usage and the equipment load, we were within 1% as a portfolio. For individual buildings, the range was about 7% and 5%. Some buildings were outside of that, but that was the average fluctuation we had for an individual building. When we're doing energy modeling, there are 3 areas of modeling inputs. There's the physical design. This is the part that the architect and engineer are responsible for, and it's the part that we're trying to predict the performance of. But you also need to have a weather, and you need to have operations. Now the weather, when we do energy modeling, we use a typical meteorological year, which is the long-term typical year. I say typical, not average, because if you use average, every day is partly sunny and a little rainy. They use typical, so they pick the most normal June and the most normal January. And then they create this year that's stitched together from 15 or 30 years worth of weather data. But June might be from 1992, and July might be from 1997. So there was never, the typical meteorological year has never happened. It will never happen. Operations-wise, we are putting as an input what we think they will use the building as. We're not really trying to predict that. We're taking them at their word of, the owner says, well, on my current building I use X number of hours a week. You plug that into the model. The flaw that I think the LEED studies have had is they aren't updating the weather, and they aren't updating the operations. And as I mentioned, we've had quite a dramatically different April this year than we did last year. Last year in April, I biked to work almost 15 days. This year I've been able to do it once because we've had snow on the ground, and we still have snow on the ground. There's a big difference year to year in weather. There's also can be a big difference in how people use a building compared to how they thought they were going to use a building. Given our time, I'm going to jump through a couple of these slides very quickly to get to the main takeaway to this part. So as I mentioned earlier, we're doing modeling iteratively throughout the process. We first do a code-based model with a typical year and typical or expected operations, and a code-based physical design. We then estimate the energy savings based on the physical design of the design and the typical weather and the expected operations. And that gives us our first estimated energy savings. But this isn't what they've actually built. It's just what they said they're going to build. The LEED stops here most of the time. With LEED, we submit based on the construction documents, not necessarily what was finally completed and built. As I mentioned earlier in my talk, what we have found is that there's about a 10% reduction from, on average, from what we thought they were going to build to what they're going to build. Some buildings do better, some buildings do worse, some buildings do more than we expected savings-wise, but on average it's about a 10% reduction. This M3, this third model that we're doing, is the what's actually in the building and functioning. So that's what the savings should be based on. When you get to trying to compare the actual metered consumption to the predicted energy use, you need to update the model with the actual operations and the actual weather. You need to replace the original code calculation with this new calculation based on the actual weather and the actual operations. And what happens if you don't? You can end up with a building that is using more energy than you thought it would, but actually saving you more energy than you thought it would. So M1 here is the code base during pre-construction, what we thought the code base was. M2 is what they told us they were going to design, and M3 is what they actually built. So the difference between M1 and M3 is what we counted in the utility program as the energy savings. This is what we normally think of as savings calculated by energy model. M4 and 5 here show that this building, M5, is using more energy than we thought, more energy than M3 predicted. And this is actually an example from this is actually the building I mentioned earlier, where it was a speculative office building that we didn't think they were going to be putting in data closets. Well, the actual energy consumption is quite a bit higher, but the code energy consumption is even higher still because they're using that building enough differently than we thought that the savings is actually higher. The other way to think about this is just because you buy a Prius doesn't mean you will pay less in gasoline. If you buy a Prius and take a job that's twice as far away as your last job, you're going to be driving it further. And you might be grumbling, well, I'm not really saving any money because I'm spending more on gas than I was before. When in actuality, you're saving twice as much as you thought you were going to save because you're driving twice as far. The opposite can happen, where the building energy consumption is less than you thought it was going to be, but the savings are also actually less because you're not using the building as much as you thought. So when we do these studies as an industry and look at what the energy consumption is and compare it directly to a lead model without updating the weather and the occupancy, two things that we're not trying to predict, we're just trying to hold steady between the baseline and the proposed, we're not really accurately telling whether or not the model worked. To sum that up, we sometimes say around our office, the phrase compared to what isn't necessarily rude. It depends on how you ask it. So when somebody says, well, these buildings aren't doing as good as we thought they would, we need to make sure we're making the proper comparison. I'm going to, okay. So when we looked, we did a two-phase study to look at, with Alliant, how well we were doing. Phase one, we were looking at 14 buildings, and we were just updating the weather. And we found the energy models used 98% of what the meter actually said. So the meter was using 2% more energy, total site energy, than we thought they would, which is pretty close when you consider what we're doing and trying to do predictive analysis. At the second phase, we looked at 10 of the 14 buildings. We narrowed it down based on buildings that we could walk through the buildings and talk to the occupants, interview the occupants to find out how they were using it hour-wise, were the equipment loads proper, and just kind of see if by adjusting those things, plug loads, exterior lighting, building operations, how accurate we could be. What we found here is that individual projects did fluctuate, but overall we were within less than 1% of we were less than 1% deviation from the actual meter with the energy model, which implies that there is not a bias. We're not getting a bias of either over-predicting, under-predicting. When we broke that out month by month, the shape generally matched pretty well. There's a couple of months where there's a little more disagreement, but overall we're matching that month by month. Natural gas, only 4 of the projects had natural gas, and we were within 10%, less than 10% difference. And the natural gas prediction wasn't quite as good as the electric prediction. To summarize, we think modeling, when you make the proper comparison, can be very effective at predicting energy consumption, and over several buildings is very, very effective at predicting energy consumption. There will always be some difference between the energy model and the actual building, but we can make that gap very, very small. To put it blithely, the model is perfect. And to some degree, that's its flaw. The model is assuming that the people are well behaved and show up at the same time every Monday or whatever the schedule you have built into it, but the model doesn't have the stochastic behavior that real people have. The model is assuming that the variable frequency drive is working and that the air handlers can meet their set points and all of those things. So we're going to always have a little bit of variation. And depending on where you are in the design, there's going to be more and more, there's going to be more or less variation. But as we learn more about that building, and we can get very accurate in predicting its energy consumption. And even early on, we can be within 20% of the energy consumption, even before the design is complete. A couple of takeaways when we did this study, what we found was, on average, the buildings were being used 10% longer than we thought. On average, they also had 10% more plug loads than we had thought. We think what's happening with that is that when you build the new building, a lot of the functions that used to be distributed across several buildings come to that new, nice, shiny building. For a school district, for instance, the PTA is going to more likely meet in the new building than the old building if they have a choice. And so we're adjusting our schedules to try to reflect this. And then lastly, if you're not measuring how close you are coming to the predicted energy consumption with the adjustments that we talked about, you can't really manage that energy consumption. That we need to tie modeling back to the operations of the building to close that loop so that the operations of the building informs the modeling of future buildings, and that the modeling of the building informs the operations of the building. So thank you very much for listening to me. I'd like to open it up to questions. I think we probably just need to have anybody who has a question to come up and talk into the microphone of the laptop so I can hear them.